This is a little bit loud, is it? All good? Okay. Yeah, thanks for being here. So many of you, so close. I'm Carsten from the University of Virginia, and I'd like to discuss with you today and inspire you perhaps to join our efforts of analyzing the security of certain hardware tokens and breaking them. Work I've been doing with Starbuck for a couple of years now, who is just ingenious in working with these. Is this breaking? The noise is breaking? It's good? Okay. Starbuck is just ingenious in working with small hardware tokens and getting all the little secrets out of it. And I'm just giving a little structural advice here and there on how to analyze them further. So a quick summary and the last chance to leave. We'll be looking at hardware tokens such as RFID tags and explain how to get the security functionality out of them, and then to analyze it and to find weaknesses. To inspire as many of you as possible to join our efforts to also reverse engineer hardware tokens, but I'll also give pointers to others in the room that might be interested in building hardware rather than breaking it, things to avoid and how to make hardware security better. We are interested in this topic because we see a lot of critical infrastructure, more and more critical infrastructure relying on hardware tokens for the security, be it access control into governmental buildings, be it passports, for instance. There's a lot of non-critical infrastructure too that's secured by hardware chips, TV, for instance, or your printers. Make sure you pay a lot for your printer cartridges through verifying that there's a tiny chip in them, and so forth. And we get the impression that in all these applications, including the critical ones, not much thought is given to making them secure enough. And that might be because the domain of hardware is hard to reach or hard to understand, but it's getting easier and easier to understand, and hence easier to break, and we provide the breaking, and hopefully somebody else will make the design better. By security, obviously, we don't mean a binary property that a system has or doesn't have, but rather an accumulation of properties where the weakest link of the entire system defines the system's security. So even something unbreakable can be circumvented if another component of your system is weak. Applications will be dealing with here as examples include, for instance, an RFID card that opens a door. So this card will know some cryptographic primitive, a cryptographic cipher that's also known at the door, and they'll both share a cryptographic key. And the card, through some protocol, will prove to the door that it knows the key, and then the door will open. Similarly, in satellite TV, for instance, there's a cryptographic cipher and a cryptographic key used to decipher the signal that comes down from the satellite, and hopefully only whoever paid for Premiere can watch it. So all these applications and all the hardware security applications rely on either a cryptographic cipher or a cryptographic key to be secret. So there must be something that only your customers know, that only your employees know, or their respective cards know. And in hardware security, the mistake is often made that both of these are kept secret and that the security is spread across the two. When cryptography, we very much rely on the cryptographic key that it be secret, where the cryptographic cipher should be some published standard, and it ought not to be secret because people like us reverse it from hardware. So that's what we're going to talk about today, breaking cryptographic ciphers by simply finding them. And since any cipher that isn't standardized is usually weak, we then normally break it within a few days. So I'll walk you through the different steps needed, and I'll try to stress how simple each of these steps is and how little tools are needed. If there's any doubt about it, we can discuss it at the end, and I'll make sure everybody leaves the room with the understanding that you too could be reverse engineering tomorrow. And if time permits, we'll look at some of the impact we have had and potentially interesting application that one should be looking at next. A microchip, as you'll find it in a smart card, will look something like this. It's an Infineon 66, which you can always tell by these two triangles here in the middle. Most of this chip area is memory and security. So the actual microchip is really this middle part. And it's a somewhat secure microchip because everything that is stored in these memories is encrypted. If you were to just read out the memories, you don't learn anything. But in order for the processor to work on the data that is stored in the memory, it has to be decrypted. So there's a memory encryptor-decryptor unit, and everything that's read in memories first goes through here and is then processed in the processing core. How do we break this? Well, easy. If it's decrypted here before it goes in here, we wiretap little wires in between here. And these are exactly these wires. So we use tiny needles, poke in there, and we see the bits flowing by. Now, the manufacturers of these chips obviously know that we can do that we can understand that chips that they build very structured. To understand themselves, these chips have to be debugged. So not trying to hide anything in silicon, because nothing can really be hidden. Everything is there once they give you the chip. They come up with other security mechanisms, such as meshes. A mesh is simply a long snake of metal going all across the chip. And if the two endpoints of the snake are not connected, the chip won't start decrypting. So if you start scratching this mesh to get to where your needle has to be put down, the chip won't decrypt anymore. Well, what do you do here? You get away with the mesh with hydrofluoric acid, and you put two needles down where the mesh should be connected, and connect those two needles. Now, with a certain needle, you poke on the data bus, and again, you read the data. This game has been going on for a couple of years now. FlyLogic has been taking apart every single chip, I think, that they've ever gotten. And this game ultimately now led manufacturers to start adding secret algorithms to their chips. So they know that we can see all the data flowing by, but what if everything is encrypted in a way that nobody has ever seen before? And that's what has been going on in the microchip domain, and this is exactly what we are breaking, just as we have been breaking the MIFARE chip. So we want to reverse engineer these very secret algorithms from the chips. So first we need to get to the chips, which usually is trivial. This, for instance, is an RFID ticket from the Moscow Metro, and the chip is in between these two antenna connectors, so it's a square millimeter about of a chip. To get to that chip, we throw it in acetone. The acetone dissolves the plastic around and either gives us the chip or gives us a small epoxy package where the chip is in. We throw that epoxy in nitric acid and we get the chip. So that step is fairly straightforward with household chemicals. Inside the chip, which is where we want to get to, we find structures like this. We find transistors built on top of a silicon substrate, and the different transistors are connected through these metal bridges. So each transistor is a little switch, and these metal bridges connect to different switches, and if you know anything about VLSI, you know that you can build an entire Intel processor using only these components. We want to take pictures now of these structures and reverse engineer the circuit that is described by them. And so we first want to take pictures of all the metal layers and ultimately of the transistors. And for this we need to cut through these different metal layers. So we basically have to cut through here to get to the transistors, for instance. This might look like they are free-flowing in this picture, but that's only because what is in between here is glass, silicon oxide. That's why you can nicely look through them. But often if you look from the different things block the view, so we really have to scrape them off, which is what Starbuck is doing with his bare hands and with some sandpaper, or preferably polishing paste. So he takes a tiny microchip and he starts polishing the microchip, sometimes using a polishing machine, and off micrometer by micrometer to get to these different layers. Sometimes the chip tilts a bit, and he cuts through different layers at the same time, especially if the chip is very small. And he came up with this ingenious idea of just putting it with the plain backside, glue it to a block of plastic, so you have something bigger to work with. And then again, he's polishing micrometer by micrometer. And next, we take pictures. Another way to get off these layers is by using hydrofluoric acid again. A little nasty to work with. If you get it on your skin, it will not actually hurt until it starts eating your bones, from what I understand. So, well, we have been working with it a bit. And it's a nice addition to the polishing. It has some different properties. So what the hydrofluoric will do is it will eat the glass in between the layers. And then these metal bridges that we have seen, they kind of break off the chip, especially if you polish them a little bit. So it's nice to combine this with polishing, but polishing has had better results for us, surprisingly. So however you get your layers off, you need to take pictures next, and we have been using a very standard microscope mostly, something you'll find in a high school lab. A normal optical microscope, not too high magnification for the feature sizes we're looking at. FlyLogic, for instance, is using a confocal microscope, which has advantages because a confocal microscope shines light at different depths and then pictures only one depth at a time. So you get your picture nicely colored by depth, and it will look something like this, where you can tell that different lines are on different depths, so on different layers of the chip. And you can also look, for instance, up here, we have some glass left over in blue, where you can look through that glass. And the normal microscope would... so if you have access to a confocal microscope, it will get you beautiful pictures. If not, don't worry, we have been using normal microscopes all along. So this is how you get pictures. Any questions, though? Is this clear? How you polish away microchips, how you take pictures? Easy, huh?
Do you polish a little and then look and then polish some more?
Right. Yeah.
Yes, check.
Exactly. The question was how we know when to stop. We just keep polishing bit by bit, and we keep checking until it's deep enough. Well, next we need to stitch those various pictures that we take off the chip together. And we borrow a program, Huggin, from Panorama Photography. So we tell it this is a panorama, this is viewing, say, east, and this is viewing north. Please stitch them together. It will either automatically or manually assisted find reference points that it thinks correspond in each picture. We'll then stitch them together. So we do that for maybe up to 100 pictures to get one consistent view of a chip, one layer. And we do that for each layer, and that's all the input material we really need. Easy, huh? We'll get pictures out of this, of the transistors at the very bottom. On top of the transistors, they are grouped into logic cells. A logic cell could be an AND, an X, or any of that. And then those different logic cells are connected through these metal bridges on various layers. And then sometimes there's also a visual cover, so people can't reverse engineer it. These logic gates on the second layer from below. To understand them, you need a tiny little bit of VLSI. So this one, for instance, is an inverter. Consists of two transistors. There's one here and one up here. Each of them has 3 connectors. So these are the transistors. And and the inputs to the transistors are connected to each other. The one will let current through when the input is high, the other one will let current through when the input is low, and they're conveniently connected to power and ground. So if you do the truth table, you'll see whatever you put at the input, the opposite will come out at the output. So it's an inverter. Every other logic gate will be similar to this. This is one with four transistors, and if you look at how they're connected to each other, you'll see that the truth table gives you a 2-NOR function. And you do that for every gate. And how long does it take to understand these, starting from scratch, Starbuck? Maybe 2 days? 2 days, yeah. So after 2 days, you should be able to read these and all the other ones. If you don't want to spend the time, just go to Silicon Zoo. We already put a nice collection of the ones we have, and we'll be uploading constantly more. So it's a good exercise to try to understand these. If you don't want to spend the time, go to Silicon Zoo and download some collections there. So we now understand how we can look at the logic gates and understand what they are. What we don't do is search all across these 10,000 or so gates and try to figure out which is which. So we wrote some MATLAB scripts, and the MATLAB scripts, they use face recognition algorithm. So we tell the MATLAB script, hey, look up here, there's a face. Where are other faces in this photography? And it will find other faces. And then we'll tell, okay, here's another type of face. Find similar faces, and it will find this again. And so just after a few clicks, we get a nice coverage of the entire chip. And it will tell us what logic function is where on the chip. Good so far? So we get a map of what logic function is where. Next step is clearly finding how they're connected to one another. A step that Starbuck again spent a lot of time on doing, especially debugging, to build a ground truth for us so we can automate this step. But conceptually, what you do is you start at some point where you know this connection has to be connected to some other gate. And you trace it across different layers until you hit some other connection. And then you know that this 2-NOR is connected to this flip-flop over here. He did this couple of thousand times total. And we now have nice ground truths to train our program, which has been written by Nitram. Nitram here anywhere? No? Nitram will be releasing software very soon, which I'm very excited about. So Nitram software is taking this image on the left and finding the different metal wires and the connection between the metal wires. So it's basically giving us this extra information, what is connected to what else. His software also does all the other things that my MATLAB scripts are doing. I was going to release all the MATLAB scripts, but his so much nicer. We'll just wait the next week or two until this is ready. I'm definitely excited about it. So we have a map of where everything is on the chip, and we know what is connected to what, which gives us a circuit plan, right? And the circuit plan is basically equivalent to source code. It's very messy source code because it wasn't ever meant to be read back, but it's nice enough for us to understand the functionality behind it. Is that clear so far? That we can find the circuit just from polishing Simple Microscope, few open source programs? Good. There are a few things that people tell us would prevent what we do, and I'm just going to go through this list to make sure it has been mentioned that this is not the case. People do a lot of obfuscation in hardware design to prevent people like Chris Stanovsky from FlyLogic from just looking at the chip and telling you immediately what is connected to what. Now, our computer programs, our MATLAB scripts, they approach this problem a little differently. They start from point A and look where's point A connected to, and they see, oh wow, there's a connection, and they don't care how it's routed. Obfuscation works something like this. If you have 8 an 8-bit data bus. You just scramble all the lines. Now, if Chris from FlyLogic goes line by line, reads it out, he reads only garbage. Now, our computer script doesn't even understand the concept of intuitive wiring. It just finds what is connected to what. The same goes for dummy functionality. So in chip design, to, again, irritate reverse engineering, human reverse engineering, extra functionality is added, functionality that doesn't actually contribute to the output. Now, we start from the output and reverse engineer to wherever we expect the input to be, and we'll simply ignore the dummy functionality. Now, one feature of a chip that still does make it very difficult for us to reverse engineer is our very large chips. Mostly, though, because I'm a terrible programmer, and Nitram's program isn't ready yet, but once somebody picks up the challenge of scaling up these ideas to whatever chip you want to work with, this will scale to a Pentium easily if you want to. And I would expect in a Pentium to find very interesting bugs that will allow you to circumvent things like OS abstraction, security levels. You might be able to create your own ring, these types of things, right? So I'm sure at some point somebody will pick up this challenge, and there will be bugs. There has been one bug being found and published at Hack in the Box, I think. I don't know how they found it, but reverse engineering will allow you to find a lot more. And now there's this last thing. People tell us once you start messing with our chips, they blow up or something, they break. That reminds me only of the Da Vinci vial where some vinegar breaks, but anything short of some acid inside the chip to break the structures will not do what people think that the microchips are able to do. Sometimes a microchip will delete memory contents, but break a physical structure such as the ones we are reverse engineering, that is not possible. So there isn't really a countermeasure to what we're doing. That's the whole point. If you're not convinced yet that you should be doing this too, yes, a very brief wrap-up of the impact we had was when we looked at the MIFARE RFID chip. So we released this exactly a year, well, we announced that we had broken it exactly a year ago here at the Congress. And shortly after, thanks to Brenno, who immediately in the new year wrote about it, a big discussion took place, mostly in the Netherlands, but then some other countries following, about using proprietary encryption. Went all the way to the Dutch Parliament, for instance, where it was decided that this was not a good technology to use. And the whole outcome was just tremendously constructive in that an understanding was created how to deal with cryptography in public systems and what types of devices not to use. And the consensus today, I think, is to only ever use standard cryptography. So that's a nice outcome. But we're not quite there yet at secure systems. And I'll briefly give an outlook over what I think is the next huge security vulnerability in hardware systems. And then we can have some discussion on what you think, where this technology or these techniques should be taken. So I think we are pretty good on cryptographic functions. In the field, we still have a lot of proprietary technology, but everything that comes out new should be implementing AES, RSA, any of those, and devices are already available in pretty much any market. But once this chain, this link of the security chain has been fixed, the next weakest link, I think, will be key storage. So that there are many copies of master keys flowing around in these hardware systems. Not if you store them online, which you might think pretty much every system does, because you do it on the internet. You store your master key in a fortress, basically, guarded by physical security and protected by your best sysadmins. In hardware systems, that's not actually possible most of the time. Because if you swipe a card to get into a building, you need a response within a fraction of a second. And you can't just call into your data center, do some processing, and call back. So there are copies of the of the secret key either stored during the runtime of the device. So if the device, say the reader at your door, boots, it will copy the key from the server, often to RAM. Anybody who knows anything about cold boot attack will know that this is a terrible idea. So don't do this ever. Or the device is locked away, the key is locked away in the device in what industry calls a secret key storage or a key storage. And only a master key is locked away for the following reason. In a system with millions of users, first of all, you couldn't store a list of all the millions of keys. Well, obviously, you don't want to give the same key to every user. But then also, even if you could store it somehow compressed on your device, the list is constantly changing. So to get around all these problems, you store one master key and then derive the key for each of the users from that master key. Makes sense, right? Now, this master key has to be stored in secure hardware. And these secure key storages come in very different flavors. They come from big appliances that you'll find in banks, for instance, for the ATM network, all the way down to SIM cards. So a lot of people store secret keys on SIM cards, yes. And all of these have to rely on proprietary algorithms for the following reason. So the master key is stored in some encrypted form because you can always read out memories. And if you read out the memory of this chip that stores the master key, you don't learn the master key yet, but rather some derivative that will be different for every appliance. When the master key is needed then, it's decrypted using a decryption function that is built into the chip, but that is secret. Now we're back to proprietary encryption, which is exactly what we've been breaking all along, MIFARE and a couple of other examples. So we've just reduced the problem to one that we already know how to solve. We can get the master key by reading out the memory on these devices and by reverse engineering the proprietary encryption function that is on this device. SAM chips are none the better. In fact, these are the SIM card-shaped key storages. They have much lower security yet. Oftentimes, you'll find keys either plain text in the RAM, or you can wiretap what I've shown in the beginning. So really, there is no good solution for secret key storage. And I don't know how to build this solution. What I'm trying to get across, though, is that if you are building hardware and you are already using good cryptography, do not rely on the fact that your keys are securely stored. Try to store them in as few places as possible and prepare for the case where your master key gets compromised. Have good key rollover schemes. So that would be one advice. If you are building hardware software, prepare for failure, roll over your keys often, be a moving target in general. Layer a lot of different security functionality and keep changing it. So if any one piece of your security puzzle fails, nothing or only a very small fraction of your population is affected. Obviously, use standard ciphers, but everybody already knows that. And that is as far as I brought material, but I'd love to have some discussion with you about hardware security and about where you see the next weaknesses. But so far, thanks for your attention.
Just a small question. The SAMs, the original MIFARE chip that you mentioned, is that on? I mean, wouldn't one way of circumventing your inspection of the chip be scaling it down to a smaller process? Is there a lower limit of what size process? For example, could you reverse engineer something really tiny like the Core Quad processors from Intel?
We couldn't reverse engineer it with the tools we have, but there's imaging technologies such as a focused ion beam that can image basically anything that can be produced. And in fact, if you could produce a microchip that nobody can image anymore, you wouldn't be able to debug it. So it's crucial for the process of making a microchip to be able to reverse engineer at least parts of it. Every microchip fab will have a reverse engineering lab built into it. We don't have a FIB, but we have access to one, so we can break pretty much anything if we want, yes.
Doesn't the cost go up as well?
Does the cost of reverse engineering go up?
I mean, doesn't the cost go up as the chips get smaller? Doesn't it cost you more to reverse engineer?
Oh yes, yeah. So a focused ion beam you won't get below $300,000, whereas the microscope we're using now is about $1,000. Yeah. So it will definitely cost more to reverse engineer. But if you find a bug in a Pentium 4, I'm not sure how much that is worth anyway. Yeah. So it might be worth the 300,000 investment in the FIB right there.
I have a question. Could you implement public key cryptography in hardware?
Oh, sure, yeah, and people have.
Well, if you have a signature function and keep your private key private and not in the door opener, it would be able to make it more secure. Do you think that's an option?
Yes, well, it very much depends on your scenario, whether or not public key crypto is an option. So often what you want to prevent is that a device is being copied. If you want to prevent a device from being copied, you still have, even with public key crypto, you'll have to store some portion of the key on the chip that you need to hide from the attacker. And from what we can tell, these hardware devices are just not capable of keeping anything secret. That would be one short answer. But there are applications where public key would at least increase the security a lot, yes.
Manufacturers tend to use glue logic in their newest chips. Doesn't that make detection of logical gates much more complicated because they are not recognizable that easy anymore?
I haven't seen a chip that wouldn't have been assembled from a standard cell library. I think glue logic is really just used to fill gaps, from what I understand. Rather than building the entire chip from it. So we could take our approach one step further, where we don't say we need to first categorize logic cells into functions and then find these functions across the chip. We could, one by one, reverse engineer the functions themselves automated. We didn't need to do that yet because everything that we see is standard cell libraries, but it's just one more step in the reverse engineering. It doesn't make it very much more difficult.
Sorry, just now you were saying the automated tracing. The automated tracing that you mentioned. Just now one of the slides.
You want me to go back some slides?
Yeah, the automated tracing.
Automated tracing, yeah, hold on. Here we go.
So you have a software that helps you to trace out all the traces.
Exactly, and this is a very old screenshot. You'll see that it actually made some errors. This dot, for example, wasn't recognized. Same here, same here. We have much better accuracy today, from what I understand. Yes, so we have accuracy close to what we need in our results, and then a few errors that are being made, they're easy to spot. But this is all automated, yes.
Then the software that is being used, what is the name again?
What is the name? Yeah. It's not released yet, but it will. Nitram from the CCC in Berlin will release his software in January, hopefully, fingers crossed. And then the name is DGETA, D-E-G-E-T-A.
Just a quick question. When you've actually done all this reverse engineering, you will have the working description of the chip in machine-readable form. Have you considered trying to simulate the chip based on this information to judge whether or not the chip behaves like your real chip does?
Yes. In fact, my answer just a minute ago, that we could automatically reverse engineering the different logic cells, that would require simulation of each logic cell. So we can simulate parts of it or even the entire chip, but it gets extremely slow. Simulating hardware in software is not efficient, and we have so far only reverse engineered cryptography, where it was very clear when we found the right function, and we didn't actually have to simulate it. But you can, in fact, if you just have the chip images, if you have very high quality chip images, you can use those as the input into a hardware simulation tool, and it will very precisely simulate it. Yeah. What polishing paste are we using? 0.0 for micrometer graining size. Is it diamond based? Silicon based. Thanks, Starbuck. Yeah, you can probably take pretty much anything you want as long as it's not too grossly grained, so you cut your chip.
Is it really as simple as you say to reconstruct the wires? Because as far as I know, there are at least like 5 to 7 metal layers to interconnect the condensators there.
That can be. I think the record is around 13, so anywhere between 1 and 13 metal layers. But once you have the process automated, it's easy to work with more than just a few layers. Fortunately, the chips we have been looking at are kind of older because they implement proprietary encryption, which has been known to not be a good idea for a while. They have had at most 4 metal layers. So the layers, they do have dedicated functions, though. It's not that most connections of a short distance would go across all these layers. They would usually come in bundles and go longer distances if they're on higher levels. So the higher levels don't add much complexity. Most complexity is always found on the lower levels. More questions?
Can you distinguish P and N transistors just by looking at the photo?
The question is, can we distinguish P and N transistors just by looking from the photos? And the answer is yes and no. So these transistors, let's look at this. These transistors, one is an N and one is a P. They look almost exactly the same, only notice that this one is bigger. The PMOS is always bigger. Depending on the configuration, that's not always true. If you had, say, 3 NAND, then the NMOSes would actually be larger. But because you know it's a 3 NAND, you expect that, and you can still tell which is which. Plus, they're always nicely separated. So P is always on top, and N is always below.
I'm wondering, actually, there are very small structures, and if you're going there on an angle, is there a problem that you might actually see several layers at once, so that you see layer 2 and 3 or something like that?
That is a problem in the polishing, yes. So if you are not super careful in the polishing, you will see this is the silicon substrate. Here are the transistors, and up here, that's the logic layer function. So the cut was diagonal through the chip, and you did damage several layers here at the same time. The goal is always to be as planar as possible to the backside of the chip, so that you only ever see one layer at a time. If you don't get that perfectly fine, that's cool too, because once you have enough pictures from one layer, and then maybe across different cuts, you can still reassemble it. So you don't, in your first cut, have to get everything down to one layer. You can, with your next chip, try again, and eventually you'll have full coverage of each layer. Does that make sense? Cool.
Have you seen any nice chip art?
Say it again?
Have you seen any chip art?
You haven't seen any what?
Chip art.
Oh, chip art. No, well, I'm not an artist, and would you call yourself an artist? Maybe a little bit? Okay. No. But, yeah, we'd love to help anybody who wants to pick it up.
What's the structural wise of this chip, the technology?
It's like 380 nano, I think. So it's fairly old, yeah.
Okay, thanks.
Have you ever tried to reverse any non-planar technology, like MEMS?
Yes, and in fact, this is a non-planar chip. Can't really tell in these images. They happen to be fairly nice, but so planarizing a chip means that after you put a layer down, you basically file it so it's straight again, and then you put the next layer down and you file it again. Before they started doing that, the chips became on top of the lines a little wobbly. And if we file these down, we actually see that wherever there's a line below, we have to file harder, kind of, or something is left if we file with the same strength everywhere. So non-planarized chips are harder to work with, but they're also easier because they're older and everything is bigger and it's easier to take pictures of. But yeah, we can break both. Cool.
Have you come across any chips with physically unclonable functions?
Interesting. Yeah, I'm working with one right now, and the idea of a physically unclonable function is ingenious, but the execution I've seen so far is definitely breakable. So a physically unclonable function works off the principle that the key to a cryptographic function is generated by different chips just naturally being different. Like humans are always different, even if they are twins. And so you build two chips, and where the process variation makes them different enough so they're cryptographically distinguishable. And the idea is to make them to make the differences so small that nobody who probes into the chip can find the differences, because you already broke it in the process of probing in. Which in theory would work, only the puffs that I've seen do not adhere to cryptographic principles. So you can break them without even reverse engineering what they're doing from the outside. Okay, are we all good? There's one more question in the back. There's two more, so two more questions, and then we'll all have dinner.
Hello. So what would you do to secure the chip?
Good question. Let me cite Chris Tarnowski here, who has been breaking microchips for at least 15 years. He says everything helps, but nothing is perfect. So try to be moving target, try to have as much different security types in your chip as possible, and keep replacing them. There's this company NDS, they make satellite smart cards and sell them kind of expensively. Every batch of their chips, from what I understand, is somewhat different from the batch before. So without being broken into, they never manufacture many chips of the same type and just keep moving, so nobody has a huge incentive to break them, because you can only ever break a small number of chips. That's probably the best advice I can give, but nothing is perfect. Okay, the question in the back?
Yeah, I think there's a high degree of automation in your image analysis. Have you considered using the acquisition maybe with CNC
Yeah, so the question is, have we automated any part of the acquisition of the images? And sure, taking the images doesn't take all that long. Taking all the different images with a stage that automatically moves, which we're already using sometimes, takes maybe 5 minutes. So the polishing will be a bottleneck, the getting just right to the right layer where you want to be. Yeah, and I'm not sure how much you can automate that. If you could maybe build a robot that puts it in HF for 30 seconds and then takes images and then does that. Yeah, we haven't automated that yet, no. Okay, well, this has been fun. Thanks a lot for all the questions, and have a good evening.